I got these. I got an old account that I created at the D-Wave system when I started the channel a year ago, and I just logged in. Because what we're going to do today is we're going to go ahead with our BS exploration of the D-Wave stuff, and so I wanted to kind of, see if I can get started with it. First, let's try to figure out how do we work with these at all, like before we really jump into actually implementing the paper, right? So I remember the demos. I think this hasn't changed. Some examples and some resources. I do have, I'm on a trial plan. I don't want to pay. I definitely don't want to pay. So what is these? Free developer access. Provide your GitHub details and you can use Leap Cloud Resources to develop and share applications. Contribute at least 100% with an original project to the open source community each month. Flexible access using any combination of up to 1 minute of direct access to D-Wave QPUs, up to 2 minutes for access to D-Wave hybrid solvers. Okay, so maybe let's do these. So this is a free, okay, commercial access. What does this give me? Access to D-Wave, increased access to the hybrid solvers, which I don't know what they are. Community email support, no obligation to open source. All software developers and developer access must be contributed to the open source community. That's nice. Research and education. Learn about instructor access and course content. Is this thing here? Just want to make sure the audio is being recorded fine. I'm constantly panicking the audio is not fine, but the audio should be fine. Anyway, so I'm gonna go ahead and choose this plan. So submit GitHub info. Maybe I should do this on another screen just in case I don't want to leak any of my GitHub data in here. Oh, okay, so I have to actually have to do this like that. I'm going to put the username repository link. So I should probably go and create a repository, a repo for these. So github.com, we're going to create a repo. I'm going to create a new repo called portfolio D-Wave, right? So portfolio optimization D-Wave, and we're going to create that repository and the portfolio. I think it's I can now copy paste the URL into the repository link, submit GitHub info. Okay, so now it seems like this is done, is it? Okay, yeah, now I have a developer. Okay, cool. So let's see, I bring that back to the screen. Now I have a developer plan. There's some online learning community and whatnot, connecting to cloud services. Then we have a solver. What is a solver? The front end of the GPU and of a solver is hybrid. Okay, so this seems to be just a bunch of solvers you can access to, and also a QPU. I don't know what we're gonna need though. I don't know what we're gonna need for the portfolio optimization problem. Explore our examples. I thought I opened that in another screen. Did I? Okay, nurse scheduling, QBoost clustering, pipelines, knapsack factoring, map coloring. So there's basically a bunch of examples. In Leap IDE, what is these? Contribute Leap community. IDE workspaces. create your workspace. Here's how to create a workspace in libID for web-based development with a GitHub repository. Point your browser to some GitHub repository, pull request, branch, or issue, prefix the URL in the address bar of your browser with these. Example, blah. This will launch a workspace container for you in the cloud containing a full Linux system and Ocean tools. It will also clone the GitHub repository branch based on the GitHub page you are coming from. You can also create your own workspace using our template or one of our example projects. Okay, so we can, but maybe we can start with a template, to be honest, rather than just using the. So that's what I saw there, I guess. So it seems to be fairly, okay, so open template in libID. What is this? Okay. Starting. It seems fairly straightforward to get started with it. That's actually nice. But I haven't really gone through the resources since I started, and I really don't remember anything of the, what the D-Wave stuff was supposed to do. If I go back to resources, no. Demos, documentation, tools, learning, interactive demos, online resources. How to solve various types of problems in the Leap platform and Ocean toolset, glossary of terms, YouTube. Maybe these. So this is still loading. Okay, so this is open now. So, okay, we've got basically, this kind of looks like Visual Studio Code. So interested in contributing a code example, please let us know about your code example by submitting a new issue to this repository. Thanks. Okay, so this is it's a sample README file. Okay. Okay, so it's just dummy stuff. The requirements txt file, a tests folder, Circle CI. This is like deployment stuff, isn't it? And then there's a Python file. Please name this file. Fill in copyright, add demo code below, format code so that it conforms with PEP 8, PEP 8. Okay, but there's nothing else here other than just like a bit of structure in terms of project structure. And we've got open workspace, edit selection, debug, terminal. New terminal. Okay, but pretty much I'm left like with no idea what to do so far. Other than, okay, so problem solving handbook. Okay, so maybe let's go through this quickly. Provides guidance on programming the D-Wave system, including how to formulate problems, embed, and configure parameters. So quantum computing has the potential to help solve blah, 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 blah. For quantum computing, as of classical, the first step is to express it in mathematical formulation. Compatible with the underlying physical hardware. D-Wave system solves problems that can be mapped into an Ising model or a quadratic and constrained binary optimization QUBO problem. The Ising model is these. with these being an objective function of n variables corresponding to physical Ising spins, where h are the biases and jij the couplings between the spins, or a QUBO is an objective function of n binary variables represented as an upper diagonal matrix, where diagonal terms are the linear coefficients of the non-zero off diagonal terms and the non-zero off diagonal terms, the quadratic coefficients. Linear coefficients of what? The map problem must be formulated to be compatible with the constraints of the physical system and as robust as possible to analog control errors. So what was the paper? Chicago quantum portfolio optimization D-Wave. I forgot what the paper was. I think they were doing this one. I think they were doing QUBO, right? So we better just and take a look at these a bit more in detail. Guidance steps, and then the formula is the process of lumping problems into the. Okay, so formulate the problem to support formulation, decompose and allocate to classical and quantum resources, and bet on a QPU or configured QPU. So intended audience, blah blah blah. Notation: vectors are indicated in lowercase bold font. Matrices are indicated in uppercase bold font. The Euclidean inner product of vectors is indicated with angular brackets. Abbreviation, Spanish quadratic program, conjunctive normal form, blah, 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 blah. So a bunch of mathematical shortcuts, key terminology. Okay, we'll come back to these if we need to. Related documents. Okay, good. Two illustrative examples. Let's go ahead. Oh, I remember doing these. The color mapping thing. Okay, so they map it as a which expresses as a cubo in scala notation. Looks like the Ising model though. Blue. Okay. That's a long document. This is an interesting description getting started with the web system. Toy problems. Maybe I should take a look at these first. Okay, we know map coloring, formulating the problem. Each region is assigned one color. Only of C possible colors, the color assigned to the one region cannot be assigned to adjacent regions. Solving the problem means finding a permissible value for each of the variables. Solving such a problem on the DOF system necessitates additional steps due to the following considerations. The mathematical formulation must use binary variables because the solution is implemented physically with qubits and so must translate to spins -1 + 1 or equivalent binary values. Okay, so I get it. So what this basically means is that I guess to quadratic because the problem's parameters are represented by qubits weights and Kepler strengths on a QPU. The formulation should be sparing in its number of variables because QPU has a limited number of qubits and couplers. Alternative formulations may have different implications for performance. The point is, okay, it must use binary variables because that's the way the machine works. So I guess what you want to have is something like for each available color, you want to have in the region you want to have like a binary string that has all zeros and then a 1 in the color that is going to be used. And then to mark the adjacent constraints, you want to have to quadratic. Okay, these I'm not like fully. In particular, the D-wave system solves problems by minimizing an objective function which expresses a QBO in Scala notation is a QBO, and Scala notation is where A1 are the biases or weights for each qubit, and qubit Q sub I and B sub ij, the coupled strengths between qubits. I guess these Kepler strengths are going to be, I guess this is what indicates whether the qubits are related. So I guess we can, or kind of connected, and I guess we can use that to say, okay, those two regions are adjacent or not. And the map coloring problem is solved by setting biases and couplet strengths such that the qubits in the minimized objective satisfy the constraints on coloring for all regions. Okay, so we have blue, green, red, and yellow. Unary encoding. Okay, yeah. So okay, so now we're basically going to have, so you're basically going to kind of build a two-color problem. The constraint that region be assigned a single color only. There, here the C equals 2 colors are unary encoded, with allowed states being either blue. Okay, so this means naturally with this encoding, you can have two colors at once assigned to a region. So this is kind of implicitly covered. And QBO format for 2 qubits, each with its bias and a single couplet between them. What is the couplet? PG. Table 6, all possible states for a single region. QPNG 00 violates 01 meets AG, 10 meets AB, 11. What does this mean though? They've got two colors. No. So this is two colors, okay. Okay, 0 and 1. Or green selected. Now QB is the color, okay. So, yeah. Violates, I don't know. I don't understand. I mean, I understand what they mean here, but like, whatever. The two color can be easily expanded to a 3-color problem. Possible colors are B, G, and R. The objective to minimize the QB format is, okay, A, B, QB. Okay, so for each, let's see if I can plug that in. Is this working? Yeah. So what is happening here is for each possible color that A, like it's got, we're talking about two regions, aren't we? Are we talking two regions? Mm. 'Cause, 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 Who's that? I thought we had a problem, particular device and source using techniques on the problem. This example simply maps C plus across the unary encoding. Consider for a two-color problem the constraint that a region be assigned a single color only. Okay, so this is just a way to implement one. We don't care about the countries. This is just a constraint like that indicates that only one color is possible. But why does this constraint work? So both colors are equally preferred. So setting A, B equals AG ensures identical energy for both states that meet the constraint. QB, QG equals 0, 1, QB, QG equals 1, 0. The state QB, QG 0, 0, which violates the constraint, has energy 0. So to ensure that the non-violating states have lower energy, set that AB equals AG, which is then below 0. Having set the minimum energy to negative for the valid states, setting AB plus AG plus BBG equals 0 for non-valid states like these ensures that state has a higher energy. Okay, so we're somehow setting up that valid states have negative energy, and then so non-valid states are everything that, like, okay, so then you kind of define an equation so that like you have yeah, so that you kind of have and meet these criteria. So the two formulation above can be easily expanded to a 3-color possible. So okay, so it's either blue, green, or red. So it's either blue, green, or red. And then here you have the possible. Okay, so you have either blue next to green, or blue next to red, or green next to red. So the 3 possible combinations that do not repeat, like the colors. Or I don't understand these part much. We're talking about one single country or one single region now. Okay, but the idea is the same. So the valid states only where only one color is there, or these 3, which are the only ones that have like a negative total energy. Okay. The rest have like above or 0 or above. For the full 4-color map problem, the 1 color per region constraint can likewise be simplified to blah, blah, blah. But I don't really get what's up with this B term in here. What's up with this B term? The D-wave QPU minimizes the energy of an Ising spin configuration whose pairwise interactions lie on the edges of a Chimera or Pegasus graph. For the D-wave 2000Q or Advantage, respectively, to solve a given Ising spin problem with arbitrary pairwise interaction structure, you minor embed its graph into a QPU graph by using qubits to represent missing edges. Figure 30 depicts the map coloring problem as a graph where each region is a node and matches and boards are edges. The minor embedding problem chapter describes various methods for embedding a given problem, an ocean software tools for automatic embedding, such as those in the OS system on minor. Simplified approach to constraints in the previous sections. Consider the first embedding in the context of a single region with a unary encoding scheme for color, shows the constraints of the previous 2, 3, and 4 map coloring problems as graphs. The constraints of a 4-color map problem require full connectivity between the 4 qubits, encoding the color for each region. Okay, so if we say no, I'm missing the region number. I'm missing the region number somewhat, because what's the point if we have 4 regions and 4 colors? What's the point, right? So that just describes how to embed stuff. And I want to get into the how do you represent the constraints of 2 adjacent regions cannot have the same color. A chain is formulated as a constraint. All its members' physical qubits represent a single logical qubit. Similar to the single color region constraint formulated above for a 2-color problem, the constraint that 2-qubit chain represents a logical qubit for a color. The logical qubit represented in blue shown has an objective of the form where QB1 and QB2 are 2 physical qubits of the logical qubit blue, for example, in a region embedded in the topmost left unit cell. These are physical qubits Q0 and Q4. And so you want to have okay, so you want to have, it has a similar shape in that like you want them to have a different color. And so how do you do these with more qubits? Sorry, with more colors? So I guess manageable chunks. So I guess what this is doing, coupling from neighboring regions in camera map. I still don't get that term, but I get the idea here that you're multiplying then. So this is for regions B and C. No. And it's easy to couple the logical qubits of 2 adjacent regions to embed the constraint that adjacent regions select different colors. To find a physical coupler connecting British Columbia's red qubit to Alberta's red qubit, look at a slightly larger portion of the chimera graph shown in block arcs. Clearly, these couplers are ideally positioned to penalize the state where the chains represent the same color are turned on in both unit cells, thereby implementing a constraint that adjacent regions select different colors. Denoting British Columbia's red qubit as QREBC and Alberta's red qubit as ABQR. The constraint that adjacent regions have different colors can be formulated similar to the objective for the construct. Yeah, exactly. Yeah, okay. So you want them to have, yeah. So this should work as well because it kind of it applies the same logic, right? Like if they have the same color, then you're gonna have sort of a 1 in here and a 1 in here, and then and kind of like a 1 in here, and so you're gonna have like an energy that's definitely over 0, and that's gonna be then penalized. Okay, whatever. Yeah, I don't think that was useful so far. getting started with these. Cubo. Quadratic and constraint boundary optimization is a pattern matching technique common in machine learning applications. Cubo is an NP-hard problem. Examples of problems that can be formulated as Cubo problems are maximum graph coloring, partition problem. Cubo problems may sometimes be well suited to algorithms aided by quantum annealing. Cubo is the problem of minimizing a quadratic polynomial over binary variables. The quadratic polynomial be of the form x1, xn. Okay. Okay, so the idea is you have a quadratic polynomial and you want to minimize it. And this is somewhat, and this is somehow well suited for quantum annealing, okay? But I wanted to understand, or recap at least a bit more why. What is quantum annealing? So let's go through these. I think I went through these already before. But I mean, it makes sense. So the thing is, okay, the thing is I get it. I get it that all right, I'm back. You're probably gonna notice I had to pause for a second. Anyway, so let's try to figure these, because okay, so I get the cubo thing, so I understand these. You see, somewhat like you have to figure out how to represent. you have to figure out how to represent your problem in such a form, in a way that you then your valid states are clearly separated, because what the annealer is going to try to do is going to try to find a way to get like low energy values, I guess, and the energy being the result, so sort of the parameters in here. That's my guess. And so you need to, the trick is to try to find a cubo representation of your problem, so that you can then find like what's the kind of set of parameters that minimizes that. And okay, and so if I go back to these, no, to the paper, right? So back to the paper, classical methods. I have to check whether this is chroma cast or something that it's kind of creating the lag. I hope that the voice in here is again like not out of sync like last time. I'm looking for Cubo. How to present a Sharpie ratio of growth is not computable as a cubo. The main thrust of this is, in fact, how to formulate a cubo, which, when presented to you, have similar results to classical Sharpie ratio. Consider the following. Sharpie ratio is defined both in one. Okay, so we're going to have to. Okay, so now I see. So what you're trying to do here is the trick is in how to represent the whole portfolio thing in a cubo form. And so it seems like expect a return, so, and the relative weight of the ith acid respectively. The denominator can be expressed as the square root of a quadratic form. The denominator of these, or what? So Qi is the binary representation of we're taking this acid or not. The I is the variance. Covia is the covariance term between the acid I and J. one will immediately recognize this as its initial formula. Will recognize that the Sharpie ridge is not a proper quadratic form and is not suitable for D-wave in its current iteration. We find that the Chicago quantum net score solves this problem and can be presented as a quadratic form. Okay, so this CQNS is somewhat a version that can represent in cube form, but we need to figure. So okay, so sorry, I'll need to dig into these. I'll need to dig into these later, I guess. How I get rid of these? Cool. Why is these suitable? Let's go through these. So I think I've gone through like explains how it works. This is the underlying quantum physics that governs its behavior. Okay, applicable problems. Quantum annealing processes naturally return low energy solutions. Some applications require the real minimum energy, and others require good low energy samples. Optimization problems, sampling problems, we don't care. How quantum annealing works. Okay, the quantum beats, also known as qubits, are the lowest energy states of the superconducting loops that make up the D-wave QPU. Lowest energy states of the superconducting loops. These states have a circulating current and a corresponding magnetic field. As with classical beats, a qubit can be in the state 0 or 1, but because the qubit is a quantum object, it can also be in a superposition of 0 state and the 1 state at the same time. At the end of the quantum annealing process, each qubit collapses from a superposition state into either 0 or 1, a classical state. The physics of this process can be shown visualized with an energy diagram as figure 5. This diagram changes over time as we can see, A, B, and C. To begin, there's just one valley, A, with a single minimum. The quantum annealing process runs, the barrier is raised, and this turns the energy diagram into what is known as double well potential. Here, the low point of the left valley corresponds to the 0 state, and the low point of the right valley corresponds to the 1 state. The qubit ends up in one of these valleys at the end of the anneal. Everything else being equal, the probability of the qubit ending on the 0 or the 1 state is equal to 50%. We can, however, control the probability of it falling into the 0 or the 1 state by applying an external magnetic field to the qubit. This field tilts the double well potential, increasing the probability of the qubit ending up in the lower well. The programmable quantity that controls the external magnetic field is called a bias, and the qubit minimizes its energy in the presence of bias. The bias term alone is not useful, however. The real power of the qubit comes when we link them together so they can influence each other. This is done with a coupler. Okay, so the coupler is what kind of puts qubits together, and then this is maybe the annealing counterpart of entanglement, or a coupler can make two qubits tend to end up in the same state, both zeros and ones, or it can make them tend to end up in opposite states, like a qubit bias. The correlation weights between coupled qubits can be programmed by setting a coupling strength. The programmable biases and weights are the means by which a problem is defined in the D-wave system. So when we use a coupler, we are using so this coupling strengths is what is gonna allow us to kind of define whether we want them to end up. When we're using a coupler, we are using another phenomenon of quantum physics called entanglement. Yay! I figured it out. When two qubits are entangled, they can be thought of as a single object with 4 possible states. Okay, that's a bit showing a potential with 4 states. Each course that's a bit different than I would define that. So it seems like entangled in this case, what they mean is like that they are sort of part of a system. Because I thought that's the idea, is that when they are entangled, sometimes you've got like things that they can just happen like a Bell state, right? Like you have the 0, 1 and 1, 0 where states can happen. The relative energy of each state depends on the biases of qubits and the coupling between them. During the anneal, the qubit states are potentially delocalized in this landscape before finally settling into 1, 1 at the end of the anneal. So you have seen each qubit has a bias and qubits interact with the couplers. Via the couplers. When formulating a problem, users choose values for the biases and couplers. The biases and coupling define an energy landscape, and the DYF computer finds the minimum energy for that landscape. This is quantum annealing. As we add qubits, system gets increasingly complex. With 2 qubits, we have 4 possible states to define an energy landscape. At 3 qubits, we have 8. For each qubit we double the number of states over which we can define the energy landscape. In summary, we start with a set of qubits, each is representing state 0, 1. They can couple when we undergo the quantum annealing. Couplers and biases are introduced, so you kind of entangle the thing and create the energy landscape. At this point, the system is in an entangled state of many possible answers. By the end of the anneal, each qubit is in a classical state that represents the minimum energy state of the problem, or one very close to it. Why does this have? Okay, so I understand the concept. I remember. I mean, I kind of I'm feeling like I just refreshed it from the videos a year ago. The section, okay, some of the physics that go into the wave thing. Classical Hamiltonian is a mathematical description of some physical system in terms of its energies. We can input any particular state of the system, and the Hamiltonian returns the energy for that state. For most non-convex Hamiltonians, finding a new energy state is an NP hard problem that classical computers cannot solve efficiently. For a quantum system, a Hamiltonian, so this system, sorry, as an example, I skipped this. As an example of a classical system, consider an extremely simple system of a table and an apple. The system has 2 possible states, the apple on the table, the apple on the floor. The Hamiltonian tells us the energies, from which we can discern that the state with the apple on the table has a higher energy than when the apple is on the floor. For a quantum system, a Hamiltonian is a function that maps certain states called eigenstates to energies. Only when the system is in an eigenstate of Hamiltonian is its energy well defined. Okay, yeah, makes sense. When the system is in any other state is uncertain, the collection of eigenstates with defined energies make up an eigenspectrum. Initial Hamiltonian, final Hamiltonian. Initial Hamiltonian, the lowest energy state of the initial Hamiltonian is when all the qubits are in a superposition state of 0 and 1. This term is also called a tunneling Hamiltonian. Final Hamiltonian, second term, the lowest energy state of the Hamiltonian is the answer to the problem. As we anneal, we introduce the problem Hamiltonian, which contains the biases and couplers, and we reduce the influence of the initial Hamiltonian. Because I remember reading that somewhere where it's like you're going from one Hamiltonian to another, or something like these, but I can't remember where I read that. When I was searching about the trotterization and stuff like this, I think. The plot of the eigenenergies versus time is a useful way to visualize the quantum annealing process. The lowest energy state during the anneal, the ground state, is typically shown at the bottom, and any excited states are above it. Certain factors. So I'm trying to understand why the cuboform is the one that's suited for the annealer. As anneal begins, the system starts at the lowest energy state, which is well separated from any is introduced. Other energy levels may get closer to the ground state. The closer they get, the higher the probability the system will jump from the lowest energy state to one of the excited states. There's a point during the anneal where the first excited state that will be the lowest energy apart from the ground state approaches the ground state closely and then diverges away again. The minimum distance between the ground. ground state and the first excited state throughout any point is called the minimum gap. Certain factors may cause the system to jump from the ground state into a higher energy state. One is thermal fluctuations that exist in any physical system. Another is running the annealing process too quickly. An annealing process that experiences no interference from outside energy sources and evolves the Hamiltonian slowly enough is called an adiabatic process. And this is where the name adiabatic quantum computing comes from, because no real-world computation can run in perfect isolation. Quantum annealing may be thought of as the real-world counterpart of adiabatic quantum computing, a theoretical idea. In reality, for some problems, the probability of staying in the ground state can sometimes be small. However, the low energy states that are returned are still very useful. Figure 8 shows the evolution of the energy functions over time while physical temperature remains constant. This chart plots energy divided by h in gigahertz, where h is the Planck constant against S, the normalized anneal fraction. It's an abstract parameter ranging from 0 to 1, whatever this is. It's a curve, tunneling energy. This is getting too complicated too quickly. Annealing controls. So maybe Wikipedia is gonna quantum tunneling E-wave implementations. Quantum annealing is a meta-heuristic for finding the global minimum of a given objective function over a given set of candidate solutions by a process using quantum fluctuations. In other words, a meta procedure for finding a procedure that finds an absolute minimum. Process solutions using quantum fluctuation-based computation instead of class computation. Quantum annealing is used mainly for problems where the search space is discrete, with many local minima, such as finding the ground state of a spin glass or a traveling salesman problem. It was formulated and is present by quantum annealing in the transverse Ising model. Quantum annealing starts from a quantum mechanical superposition of all possible states with equal weights. Then the system evolves following the time-dependent Schrodinger equation, a natural quantum mechanical evolution of a physical system. The amplitudes of all candidate states keep changing, realizing a quantum parallelism according to the time-dependent strength of the transverse field, which causes quantum tunneling between states. If the state of change of the transverse field is low and now the system stays close to the ground state of the instantaneous Hamiltonian. Okay. Also see a adiabatic quantum computation. If the rate of change of the I think the idea is that you start with a superposition of all states, and as you're introducing the weights and biases, the idea is if you do this slow enough, the system stays, but what system? Slow enough, the system stays close to the ground state of the instantaneous Hamiltonian. So the idea is, I think that's kind of the idea is you start with like an initial, Hamiltonian, right? Or a system with a system that you know the lowest energy level, which is basically if you have these pure superposition, you know there's just one minima, right? Like it's actually any of the states is a local minima, right? And so that's your like initial, right? And then you have like another Hamiltonian called like the B. That's where you want to have the local minima from, but it's it's impossible to calculate these. And I think what this kind of concept is saying is that if you're moving away from this one to this one slow enough, the system stays in the lowest state at every single step. Thus, when you're here, you are at the minimal state for this particular system. And so then that's it. I think that's the idea. Okay. If I understand this well. What is similar to annealing whose temperature parameter plays a similar role. And similar annealing temperature determines the probability of moving to a state of higher energy from a single current state. In quantum annealing, the strength of transversal determines the quantum kind of probability to change the amplitudes of all states. In parallel, analytical and numerical evidence suggests that quantum annealing outperforms similar annealing under certain conditions. I think this is it, but I'm not so sure. But I'm still not entirely sure why the cuboform is the one. Is the one that works. Like, I guess what we could do next is just go ahead and kind of, start with the implementation, but it's still, I'd like to understand why the cuboform is the one that works. Initial Hamiltonian, final Hamiltonian. As we anneal, we introduce the problem Hamiltonian, which contains the biases and couplers, and we reduce the influence of the initial Hamiltonian. At the end of the anneal, we are in an eigenstate of the problem Hamiltonian. Ideally, we have stayed in the minimum energy state throughout the quantum annealing process, so that by the end, we are in the minimum energy state of the problem Hamiltonian, and therefore have an answer to the problem we want to solve. That's what I think I got it right. Okay, but why that's the cubo? So why is the cuboform sort of the mathematical representation for these? Mm, 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 which enable a variety of searches through the energy landscape. These controls can improve both optimization and sample performance for certain types of problems. Formulation, key concepts, local minima, cubo, why cubo? Okay, so this is the cubo stuff. Linear coefficient, quadratic coefficient. I guess this has got to do with the fact that that's naturally how you parameterize these machines, right? So you have the biases. You have two parameters that you need to configure, right? Like, so the way you can configure a landscape, like the energy landscape, is to have the biases that kind of tune each qubit to be a bit more 0 or be more 1, and then you have the couplings, which basically define the entanglement between the qubits, and so yeah, and so that's kind of it's just a natural way of representing the problem. Like if that's how you can configure a machine, that's the type of stuff you can configure, right? Like so. This means if you're able to express your problem in terms of this type of configuration, then assuming the quantum annealing stuff works, then that's what you get, right? So you kind of define your energy landscape like these. You define, because that's how you can configure the qubits and the couplings. So if you're able to define your problem in terms of such constraints, then you can configure an energy landscape. But you have to be able to do it in a way that you know you're going to be able to stay to get a minimal. I feel I'm missing. I feel I'm missing, like, just one little thing to connect the dots. But I think I get the idea. You're getting the energy. You're getting basically, what are you getting as an outcome? You're getting an actual value for each qubit, right? Are you? How do you define the weights? How do you define the weights and the biases and the weights? It's part of your problem. Linear coefficient, node weight, coupling strength. And what you find at the end is you find the lowest energy value, and you get, like, so you're staying at the lowest energy level, and then you know in which states each of your qubits are. And in this case, for example, for the example of the portfolio, which portfolio is to peak. Like, whether qubit 1 like tells you peak this portfolio, so you know whether it's 0 or 1. Yeah, exactly. But still, I don't know how do you play with the parameters? How do you play with the weights and biases? I get it, but the reason you need to do this in a qubit form is because that's how you configure the machine, right? So the machine has got qubits, and so you've got to define the biases of the qubits and also the coupling strengths of pairs of qubits. Those are the things you can configure for the machine, and so this will then define the energy landscape that you're gonna have. And so, okay. So this means as long as you can translate your problem into a qubit form, then you can give it into a DOF machine, and it should give you something that works. So based on, and we're going to stay here, so you kind of introduce that, like, the whole thing, the whole underlying thing that makes it work is the fact that if you start with an initial superposition and you're introducing the Hamiltonian step by step, and you do this slowly enough, in theory, the system should stay at the lowest energy level. Okay. In theory. So basically, yeah, and then, okay. I don't know where the BS in that is, right? Like, is the BS in that the fact that this theory is just a theory and that the qubits are really noisy, maybe, and maybe. And so if you cannot express your problem in such, yeah, so it's a really purpose-specific machine, but I don't really understand where right now where the BS is, to be honest. The adiabatic, so the annealing thing. So can you, in theory, implement any problem like these. So this is just a subset of problems, I guess. Yeah, because your problem might not be expressible in such way. Okay. Okay, so we refreshed a bit of these. That's good. How are the timing? Yeah, I think it's time to go. Cool. Okay. Haven't progressed much, but at least we know the basics. Okay, so we can then start. I think the next step will really be to understand. Okay, so to understand how this is how this is being developed. Develop the cube to number of assets in a portfolio. Assets, when dealing with a single asset portfolio, we only consider linear terms in the QO. In particular, when we have lower triangular metrics or zero diagonal metrics products of the form. Blah, blah, blah. So pick off only the linear terms. So I think, okay, so if you're only targeting one asset portfolios, then you just don't need to do anything with the couplings. Maybe we can even start like this, moving to two or more assets. We have substantially more work to do. Looking at a simple asset, there are no covariance terms to deal with, and we can embed the inverse Sharpie ratio directly into the qubits. We create a unique QO for each size portfolio evaluated. Okay. Okay. I now things start to make more sense. So then for each, so if your target is to say I want like three asset portfolios, then you have a different QO. If you want like it's a bit like the color mapping thing, right? Like so you have for 3 color problem, 4 color problem. So we divide in linear terms. Find the variance terms. Okay, I gotta dig into this a bit more next time, but that's kind of it starts to make a bit more sense. Embedding, scaling, and hardware considerations. Okay, but there's no much like you know what the paper is really vague in terms of defining the actual development of the QO. So we're gonna have to put a lot of work into these, I think. But I guess that's gonna be the fun part. Okay, cool. But I guess then the couplings are gonna have to do with the covariance of in between assets, right? Because I think there is something like these with the CQNS, like you want to kind of minimize or maximize that, like somehow. I'm not sure exactly what was the goal of these, but what did you want to do with the covariance? But that's what relates to portfolios. Okay, but still, how you pick the biases? I don't know. How do you pick the biases? Okay, is it that based on historical data you pick the based on historical data you define the biases and the yeah, that's probably the way you do it. Yeah, and so you want the minimal. So I'm trying to kind of recap. Like I'm trying to, you know, do a bit of a recap before I stop the video, just to make sure that I'm on the right track. But I think so. The thing here is Sharpie ratio. Okay, but it is what it is. I still don't know. I still don't see where the BS is. I still can't. I can't even see where the BS is coming from or might be coming from. So that's a bit confusing. But I mean, you can believe the machine. Maybe it's not working as they sell it. As they sell, it's working. I totally agree on this. But at least to me, like not having the expertise, I don't really. Yeah, and it's an NP hard problem, so it's something that a classical machine you wouldn't be able to solve efficiently. especially the more variables you have in there. We'll see. Okay, we're just the very beginning. So let's see. I'm gonna try to get something coded down in the next session. Let's aim at that. Cool. I hope that was useful. I feel like I feel like it's moving slowly, but I think it's good to go to kind of move to the next step without having to get too much lost into the details in here so far. Cool. Bye bye.